probability part of this course is to develop probability models. What are the probability models? AMF, PDF, CDF, expected value, there are others, LGF, PCF, we will cover it here in this semester. And these probability models actually what do they do? They actually test the likelihood of getting a particular data from when you run the experiment. When you roll a die, actually the probability model says what is the chance that you get 6, what is the chance that you get 4. So the probability models deals with the chances of running a random experiment when you run it. This probability model actually provide the chances or likelihood. On the other hand, when we have a sample of data, statistics will actually deals with a perfect representation of the data, a description of the data, which can be a graph, which can be a histogram, which can be summary, or actually you can have some sort of inference from the data, and this inference actually will fit a model. Or fitting a probability model for the data. So now you can see sometimes we can estimate parameters about the data. So you can see these two are actually same, but in opposite direction. You have random experiment, you have sample data. Now, when we are studying probability, we are going from upward to the downward direction, and the probability model actually is providing the likelihood that we will run the experiment, what will be the data that we find. On the other hand, when we have a set of data that we call a sample data, statistical or inferential statistics facilitated to fit a probability model for this data so that you can actually infer about the experiment. When you have the data, you do not have access to the experiment, just you want to know the properties of the data, you want to estimate the parameters, and based on this, the probability model and the estimation, you want to actually draw conclusions from it. For example, in machine learning, if you use this inference, then you can actually classify things. For example, if the network data are available over a network data, then the inference can actually tells you that the data is in a particular area. When this data are available, and a scan filter can, mail filter can tell you whether the mail is strong or mail is less stable. So this classification can be done by this. Or you can draw a regression line where you can estimate a future data based on the statistical inference. Now we want to define two terms, population and sample. As we mentioned, whenever we will be actually dealing with some random experiment, then random experiment will generate data. And as here, we will start with a set of data. The collection of data that it is not the whole data. It will be always a subset of data. This subset of data is collected from bigger actually, almost infinite, maybe infinite, maybe very large. A simple example could be, let's say there is a student data in IT. Now we can have two options. One is we have a student data that consists of all 3,000 students, CGPA, students, other things, students height, students weight, many other things can be there. This data, priority, it is still gettable. Now, if you consider all students in Bangladesh, millions, then actually such a data does not exist, most of the cases. But if we want to gather knowledge about this data, then actually we need to start with a small set of data. That small set actually is a subset of the data, and we call it sample. Square. Two sides. Two sides. That's it. So what do you want to call it in the class? You should not. If it is related to if you want to leave, I don't have any problem. But Modern John is not supposed to call you during the class. What is it? Rudy? What is it? Prescription? Okay. Sorry, after 5. What do you want to stay here? You want to leave that class, I don't have any problem. But for showing a prescription, you want to jump on in the middle of a class. So, right? Do you know what John is here? He may not be here. What is Modern John available in his room? They don't know. Remote. Okay. So, the population, when we use the term population, we will consider the total collection of elements being studied. Actually, in the picture what we have a set of elements. Each entity is there with one or more a set of elements. For example, a human being, his height, his weight, his income, the amount of tax he or she pays, everything can be understood to that person. That if we actually have a collection of all these data, then we will call it a population, depending on the jurisdiction, the area for which we are defining. For example, we can have a actual population that includes all people. So 200 million people, height, weight, right? But even if you consider all living persons in the world, most of the cases, the population actually, the size is so large, we cannot count it. So, we always will consider this one actually exists, but we may or may not have enough information about this. And this is the complex set. It is not possible that like the sample space, that it includes all data. The population actually is actually to have all data. Now, the realistic one is sample. The sample actually is very complicated. Nowadays, you will find, or all the times before an election, you will find that 50% of the voters are voting towards a particular party. This actually is. You cannot actually collect the data of all voters of voters. Then the selection of voters is there. A sub-group of voters is selected. This selection actually is very much important. If this selection is random, then we say it is sample. But if the selection is biased, say if you collect majority of the person in the sample that are actually active participants of a certain party, then they will always vote for that party, and your actually sample is not the random one, and the result based on this sampling will be not correct. But if you can perfectly collect a set of random voters, then actually it might reflect the actual scenario for all actually is a subset of the population. Since the population is often too large to examine, we always will examine the restaurant population. And this one is a selected subgroup from the population. This is important. And this one. The sample should represent the population. For example, among these 3,000 students of IUP, if a sample of 20 students is actually collected, and all these 20 students represent the host characteristic, then this is not important. Because it will miss many information related to it. Even if you collect this information from 20 Cameroon students, still this sample is not good one. So what it will do? Not only it will have at least one person from this category, but also it will maintain the proportion. For example, here we have 2,000 Bangladeshi students and say 500 international students. Each of the among these 500 students, there are certain communities. So whenever we collect the sample size is important. Sample element will be selected in such a way, always there will be a proportional representative in the sample. If there is a proportional representative in the sample, then actually what will happen? This sample will represent the whole population. And the important thing is that if we collect the data, considering that this collected data actually is a value of a random variable, then actually, for example, if the data has a particular distribution, the solution has a particular distribution, that means, say, from this we can see that 80% people is most country people. Among this 500, so we have 5 communities with some distribution. So whatever we will select, if you select with this distribution, then 80% of the people will be selected from the host countries. And in that case, actually, this selected person can be considered as a head of a random variable. And that actually random variable will have the same distribution as the population. So, one more thing that we will consider that the population itself will have a probability distribution. And the sample actually is a collection of random variables. If the sample size is n, there is a collection of random variables, and each random variable actually has the same distribution as the population distribution. Then actually this sample will be random sample and it will be a representative of the population. In normal, sample is like this. A normal sample is like this. Here actually it is the collection of 15 students of a particular course. Let's say this course is introductory psychology course. Total students of this course is say 700. All first year students of IIT takes the psychology. See, like this one. Then a sample of these 50 students will be representative of the 700 students, and actually two scores are here. What is the saddest score of these students? And actually another one is the final exam score of this student. Therefore, this score actually you can have histogram, you can have many other things. Here actually two things are here. One is X bar and Y. This X bar is the average of the marks here. And we need to consider that this is a random variable. So each column of the data actually is a random variable. And this X represents X bar represents the average value, so the expected value of this bar, and here actually y bar represents the average. Also this data has this S actually now represents variance. And this S of y will represent variance of y. Now we have a conflicting notation. Previously we used the S for what? Sample space. And S of x. So set of values for x, right? Now, actually this S actually sample variance is so widely used. Most of the cases probability books are not the statistics books. So they have derived domain, statistics books have derived domain. So the probability books use this notation and the statistics books use this notation. But here we are combining these two things in a single course. Most of the universities actually the probability and statistics are a combined course. So for now we will assume that S of x actually gives the variance. Usually we call it a sample variance. We will differentiate this one sometimes. Now, whenever we have a data, we can measure the central tendency. What are the central tendency? Mean, median, mode. We are familiar, right? What is median?
The middle value of the sample space for the middle value of the sample space.
Sorry?
The middle value of the sample space where it is arranged.
Okay. When it is arranged, ordered, right? Now, question is very simple. If we have this data, if we can order them depending on the number of size of the data. If it is an even number, then actually the middle one. If it is odd number, the middle one. If it is even number, this is the middle data, and these two are middle data. The average of these two will be the middle, right? Now my question is, if we look at here, the average value is this one, right? The average value is this one. We also calculated average value. How? So the mean value can. Now focus here. Whenever we have a probability model, we can calculate the expected value here. Whenever we have a data, we can calculate the mean here. So from the data, we can calculate the expected value. From the probability model, we can calculate the expected value. This one actually is the arithmetic mean. This one is weighted, right? But both of these two represent the same. Now my question is, can we extract the median from the probability model? More specifically, if you have PMF and CDF, can you get the median of it? Say, you look at I. What is the median?
25.
If you draw the CDF curve, 1, 2, 3, 4, 5, 6, right? This is the one, right? 1, 2, 3, 4, 5, one more. Now, I discussed this quantity in an earlier class. Can anybody recall?
Complementary.
How many recipes you got that? This one actually is inverse function. So, if you have the inverse function of the CDF, inverse CDF, then a value of 0.5 here
2%.
will lead you to samples. Then you will get the actually secret. When it is given number, then 0.5 will be where? 0.16, 0.16, 0.16. And this is actually you will have one value here, you will have one value here. 0.5 will be. Then actually you can calculate the CDF. So the inverse of the CDF, if it is the CDF, if it is 0.5, then this quantity actually will give you the value of x can be calculated from here for the value of 0.5. It will return the median of the data because it will point to the median data, right? Now, here these two terms has difference. What is the difference? One is mean, another one is x. One is capital N, another one is
Small.
what is the difference? When we actually have the population and sample, then we can calculate the mean value of the population, and we have all the possible data in. Most of the cases, this is a theoretical thing, practically may not exist. For example, the population mean of the height of the IIT students will be the average height of all IIT students. But this one actually is based on a sample of size small n, you can collect a sample of 15, 20, 30, 50 students and you can measure this one. So we differentiate these two terms as population mean and sample mean. So whenever we will consider the parameter mu, we will consider the population. Now, how can we calculate the mode? Based on the frequency of the data, right? The highest frequency data will be considered as the, for example, here 733 as the frequency 6. That means it appears 6 times in the data. Whereas 785, 4 times. This is an example data. So 783 is the most frequent score. And it is 6 times we call it the mode, right? The mode of the data is. Can we find out the mode from the probability model?
Yes, sir, PMF.
We can calculate it from the PMF model. So let's consider. This is the PMF of A. And the PMF of X. What is the mode? Because if we actually elaborate this formula, then for probability is half when x is equal to 1. Probability is 1 for x is equal to 1 8, x is equal to 3. And it goes up to infinity, right? So if we generate 100 data, how many 1 will be there? On an average. 50% of them will be 1. 25% will be 2, 12% will be 3, and so on. So, the mode of the data will be, and for this, and remember y. What is the mode? 0, 1, 2, 3. Distribution is what? Binomial. And we specifically we use this example somewhere, right?
So,
4 minus y. So, what is the probability that y is equal to 0? Right? Because this 4 choose 0 will be 1. 1 over 4 to the power 0 will be 1. So 3 by 4 to the power? No, this is not. This will be what? 3 by 4 to the power? 4. So it will be 81 divided by 16, 64, use And now what is y equal to 1? Y equal to 1 will be 4 times 1 over 4 times 3 by 4 times
3.
3, 2, 3. So actually, if you arrange all the probabilities, then you will find the highest probability belongs to y equal to. So the mode of the data will be once again arithmetic. Now we can measure the dispersion of the data. How do we measure the dispersion? 3 quantifications are here. Variance, standard deviation. Another one is mean deviation. Mean deviation actually is a relative term. How do we define mean deviation? For each of these code, we can calculate the difference between the data and the mean. Xi and x bar. This is our mean. And then actually the sum of the absolute value divided by the number of data actually is the mean deviation. Okay? Variance we have already defined it. But there is a problem. The problem is when we measure the population variance sigma square, we divide the square sum by what? Capital A. When we calculate the sample variance, we divide the square sum by what? Anyone knows it? Suppose as if you want, then we will not calculate the variance. Okay? If the sample size is more, we will not calculate that because it will be significant. Now, difference is not here, the difference is here. We will actually discuss on this later also in next year, even in part of the semester. The main thing is that whenever we measure the difference based on the two average, then actually it gives us the actual difference. But whenever we measure it from sample average, sample mean, then the sample mean actually may not be the correct. Most of the cases it is expected that the difference will be a bit less. That's why the statistician, based on their experience, they find that whenever there will be sample mean here, the data will be divided by n minus 1 just to increase the value of it. If you divide it by n minus 1, then it will be larger, right? So the sample variance will be closer to the population variance. That's what it is. But this is just a convention. Okay? We know standard deviation, we talked about this many times. Now, what is a sample? We discussed sample and population, but we want to actually extract further the value of a sample. This is population. And this is sample. How samples are collected? One all together or one at a time? Or all together? That you will throw a net, whoever will be in the net, you will actually samples and collected. Just simply consider a population consists of the height of all IoT estimates. Then this height will be, let's say, from 5 feet 3 inches to 6 feet 3 inches. Let's say. Now, they are uniformly distributed. So the population has a distribution. This is uniform collect the first element of the sample. How will you collect? You will randomly choose a person and measure his. This is one. On the other hand, if you consider that forget about the population, since it is uniformly distributed, now you can generate it by random number generator. Let's say you are generating it by random number generator. Then what will happen? The generated value will be what? A random value? Or a random variable? Yes or not? So each sample, each element of the sample is a random variable. X1, X2, up to X. You understand this? Just if there is a population, it is the collection of all data. And whenever we want to draw, for example, if you want to draw the data from 1 to 6 by rolling a die, each time you need an element, you will roll a die and you will get actually all the values for. Okay, this is 4. You roll the die again, or the value is 3. You roll the die again, and the value is 1 to 6. Then these samples actually are these values 4, 3, 2, 1, 5, and so on. But if we just focus here, then we can identify that this value 4 actually is the value of the random variable. So we can have the probability that x1 equal to 4 in case of a discrete random variable. And this has the same distribution as the population distribution. If you have the same distribution as the population distribution, then actually you will collect the data that will represent the population. Say if it is uniform in between 5.3 to 6.3, and your random variable x1 is a your sample element x1 is a random variable with the same distribution. Every time you generate a value, it will be a representative of the population. That's why what we consider that each of the sample actually is a random variable. And this sample itself is a collection of random variables. So whenever we will consider a sample, we will consider that we have a set of random variables x1, x2, up to xn. Now, since it's a random variable, it will have a distribution. And the distribution of these random variables are same as the population distribution. There are other things. This sample should be IID. You can recall IID? Heard somewhere, right? So IID actually, the first line indicates independent, second line indicates identity, or other way. So if a set of random variables are IID, that means they are identical and they are independent. So they are identical and they are independent. When they are independent, then they are benefits. We have already seen that one. Now, so a sample is a collection of IID random variables, and the distribution of the random variables is same as the population distribution, right? Now, what is value of x1? We have a value, a small x1, right? We call this one sample values. So if there is a sample, then we have sample values, and if there is a sample, we have a collection of random variables. Sample values are actually the values of the random variable. So normally a sample is a collection of independent random variables having the same population distribution, and they are IID. More formal from the text, if x or xn are independent random variables having a common distribution f, then we say they constitute the sample. But this sample is from a particular population, then this distribution should be the same distribution as the population distribution. Now, we have two factors for f. F may be known, but parameters are not known. Right? That means we know it is normal, but we do not know the value of mu and sigma square. This could be one case. F may be completely unknown. We do not know the distribution as well as the parameters. Both may be known, specified. In that case, actually, we do not need to infer it from the data. Now, we move on to the part statistics. You hardly know statistics, but there is a definition of statistics. What is statistics? What does it mean? What does it mean? This means if we can define some quantity based on the collected sample, then this quantity actually is a function of sample. A sample is what? A sample is a set of random variables. Right? And if we can define any function, then this one will also be a random variable. If this random variable is actually is defined from a sample, these random variables are not actually actual random variables, they are actually part of a random sample. If actually we define a function of what? Sample element of a sample, or this one actually eventually this one will be replaced by x1 into xn. So if x is a function of the sample values, then we will call x as a statistic. And these statistics can be used to infer conclusion from the data. For example, if x bar is defined in this way, then what does x bar represent? So this x bar is average, but it is not any average, it is a sample average. We call it a sample mean. We call it a sample mean. So in this course actually, in this part of the course, we will try to understand mainly statistics. If you can define the statistic perfectly for a particular test, then actually you can have the conclusion from the test. So our one job will be to define the statistics. And the second part will be, what are the two things? One is we will define statistics. Statistics are nothing but function of sample value. We will define statistics so that we can draw conclusion. And to draw conclusion, what we need to know the distribution of these statistics. What does it mean? What do we mean by the distribution? This distribution means the probability model. Means what? PMF, PDF, mostly we will be focusing on PMF and PDF. For example, this x bar is the statistic, right? Can anyone tell what is this distribution? By the time distribution will be in what? PMF or PDF? What is appropriate here? PMF or PDF?
PMF.
X is continuous random variable or discrete? Right? Every time you will collect a sample and divide it by n, you can have any values, right? Within a range. So most of the cases it will be a continuous random. Most of the cases. And we will have a PDF. Now can anyone tell what will be the PDF of x? This PDF of x bar is the distribution of this statistic. If x is a random variable and its PDF actually is its distribution. For example, when x is normal, we say its distribution function is normal. But by distribution function different. So our task will be in this part of the course to define different statistics. And from this statistic, we will draw conclusion about the data. And to do that, what we need to know the distribution of the statistic. Can anyone tell what is the distribution of this? Say if x is normal, xi is normal. With average mean and variance sigma square. So what will be the distribution of x bar?
Normal.
What is the mean? We discussed many times that this x bar, right, is defined by sum of this one. This one is a constant, you can ignore it from now, right? Then, if you ignore this one, this small a, then what is the expected value of this summation? Mean. We told this, right? Expectation of summation is equal to summation of the individual. Right? We discussed this one many times. Then the expected value of this one is what? N mu divided by n is what? What is the variance? Since x1, x2, xn are IID, their variance will be sum of their variance. What is the variance? Sigma square. Sum will be what? N. And this n will be yes or no? No. What is it? Right? So if there is a constant product in the variance, since variance actually is square everything, this constant term will be square. So what will we have? This n will be n square. And this quantity will be what? Sigma square by? Do you understand this? If x1, x2, xn are normal, then this x bar is also normal. I guess I mentioned one term. Once normal, always normal, right? Yes or no? If you have a set of random variables or one random variable that are normal, whatever you do, they will remain normal. This is one. So that's why the normal random variables are so important. Now, this x bar has a distribution which is normal with mean, and variance sigma square. Throughout this part of the course, our objective will be identifying different statistics for different tests, for different purposes, for different estimations, and draw conclusion from the statistics. To draw conclusion from the statistics, what we need? We need to know the distribution of the statistics. So if we summarize here, one thing from the data we need to define statistics, right? So define statistics. Then identify what? Distribution. Then another one is draw. Is this clear? These are the three steps. From any set of data, when we draw conclusion, we need to define a function that will draw conclusion from the data. We call a function of this sample a statistic. We need to define the statistic. We need to identify the distribution of this statistic. And once we have the distribution, we will be able to draw conclusion, right? For example, this sample B is a statistic because it is defined from the elements of the sample which are random variables. So X bar has a distribution, right? That means X bar is a random variable. Yes or no? Or X bar is a constant. X bar is random because this sample actually is a small collection of the whole population. Each time you draw a sample, you collect the sample, it will have a different set of values and the average will be different. So each time you draw a sample and you calculate the sample mean, it will have a different value. That's why sample mean is a random variable. Right? Before going to discover the true distribution of the sample mean, we do not know the distribution of X bar. Since it's a random variable, can we calculate the expected value of the sample? Yes, we do, because we just calculated the expected value of the sample. What is that? Expected value of the sample mean is mu, right? Here is the formula. The expected value of the sample mean is nothing but the expected value of this thing. It is a sum of random variables divided by n. Since n is constant, you can ignore n. So it is the expected value of the sum of random variable, and we know expectation of sum actually is the sum of individual expectation. And each of them are IID, so they have a mean value mu. You will have n mu divided by mu n that I already have shown, which is mu. Now, what does this quantity represent? Expected value of X. Can anyone tell? It is the average of the is X1, X2, Xn. Each set of Xn produces X bar. It's an average value. And we are taking the average of the averages. What actually it is? If say we want to measure the average height of the IT student, and 10 people have been actually given the responsibility to measure the collect the sample and measure the average. So the first student will have one average. The second student will have
Second.
then the student will have. If we actually
By
take the average of these averages, then we will get what?
accepted X bar.
And this quantity is this one. And it says that if you take the average of the averages, then you will get the population average. If you perfectly collect a large number of samples and you take the average of each of the samples, then you take in the second step the average of the averages, then actually it is very likely that you will get the average of the population. And that's why the expected value of the sample will actually turn out to be the population,
Yeah.
true population. Similarly, the variance of the sample B actually is the summation, variance of the summation divided by n, and we can show that it is sigma square divided by n. So, whenever we calculate the average of the average of the sample mean, it becomes the population mean. When we calculate the variance of the sample mean, it becomes the population variance divided by n. Why? Why the n remains here? Actually, intuitively we can say as n grows, sample size will have the average value which is close to the population mean. That's why this distribution will be narrower and narrower. And eventually when this n will be n, this x bar will be what? There will be no variance. If you have a sample size equal to n, that means you have all population data to calculate the average, and this average will be, you do not need to collect many samples. It will be equal to mu, and the sample mean actually will have no variance. The variance will be exactly zero. Okay. Now, the central limit theorem, one of the most important theorem. Here, we assume that x bar is a random variable. We calculated the expected value. We calculated the variance. Expected value is mu, variance is sigma square by n. These quantities are very much important. In many problems, we need to know that. Okay. Now, question is, what is the distribution of x bar? This distribution of the x bar is actually given by the central limit theorem. The central limit theorem actually is very interesting and very simple. What does it say? It says that if x1, x2, and xn are identical, they have to be, they are independent and identically distributed. They are identically distributed and they are independent. If this is the case, then their sum is approximately what? The sum of n random variables of any type, but they have to be higher. For example, the sum of n binomial random variable, sum of n uniform random variable, sum of n any random variable will have approximately a normal distribution. So we can write the summation is normal. And what is the, if it is normal, what is the mu? The mu will be n mu, and the variance will be is this clear? So if this is the case, then we use a dot here. What does the dot mean? The dot means that this distribution is an approximation. This distribution is an approximation. Okay? So you not see it. Sure. There is a quiz after this class. Whom I ready? Quiz. What class is or exercise or what type of exercise you will prefer?
Sleeping.
বেশি ভুল করছে 10টা ভুল দাও ওই বলে এখান থেকে কিন্তু চলে গেছি just to skip but it is your usual position that I was searching
दरबार चैट में उसको क्या
है Okay. So, the central limit theorem is very simple. What it says, and what improvement actually I have observed in the earlier class. Only 9 extra signatures. 34 was present. Why are present? And 43 signatures. This time, how many?
0.
It is improving. In an earlier class, your class maybe, 25 were present and 49 signatures were there. Right? 100%. And now we have an improvement. 34 present, 43 signatures. It's a good sign, right? We are becoming better human beings. And in Bangladesh, actually, most of the Bangladeshi town, you will find a cloud here. Almost honest. What does it mean? I don't understand. A person will either honest or dishonest. But in Bangladesh, there are people who are almost honest.
70% honest.
How it becomes fuzzy? It should be bargain, right? So, under that circumstance, you are becoming so almost honest. 100% to nowadays, out of 34, 9, say 25, around 25%. Now we can say almost honest, right? It's a very dangerous term. A dishonest person actually is certified as
Almost.
now, if we consider that the sum is x, then x is normal, approximately normal with mu and n sigma square. Then what is the distribution of this? What is the distribution of this quantity? This is the standard normal, right? Why is so? Actually, we know z equal to x minus mu divided by sigma. And here mu is n mu, and this square root of this one actually is square root n sigma. So, if we have a sum of iodine random variables, then the sum subtracted by n mu divided by sigma square root of n will be standard normal random variable, and therefore the probability that this actually is less than x will simply be z is less than x, and we can use the
Table.
who can solve this problem? Solve it.
This is the lowest.
How many have time? Sure. এদের 2% করে ওকে
Almost honest.
35
Random variable you can leave.
43 I sorry still let me count 3 7 10 15 3 6 9 12 29 2 5 6 7 8 9 38 already put the sign on your behalf already what is your idea? Tell me, what is behalf already signed? Maybe one is we have already said. So now it becomes 44. See the positive. Right? See the positive thing here. Always A positive, 2 positive, B positive, B positive, half of the one B positive. In terms of blood. Anyone solve it? The problem says in a car insurance company, following clients are here. Each client may or may not claim a refund, right? If there is an accident or something like this, this is random thing. And this amount that is claimed by a policyholder is a random variable with mean what? 320 and variance. What is the distribution? Nothing. What you are asked, approximate the probability that the total yearly claim will exceed 8.3 million. If you consider the total yearly payment is X, then it is the summation of what? XL is the claim of the ith client. There are 25,000 clients. Then the total actually claim will be X. Now, what is the expected value of the distribution of X? Not known. The average, so its average is 320. Its standard deviation is 540. Now, what is the distribution of X? We did not know. But according to the central limit theorem, the distribution of X is approximately normal. It means what? Right? And the variance is? This is the variance. And what we need to calculate is X is greater than
8.3.
Can we do now? What we need to do, we need to actually write X minus n mu divided by what? Square root of n sigma, right, is greater than 8.3 into 10 to the power 6 minus, what is this one? 8 into 10 to the power 6, right? Divided by what? Square root of this one is, close the text, 8.53, 8.10 to the power 4. What is this? This quantity, according to this definition, this quantity is standard normal. So we can write here actually this probability that Z is greater than, from the text, which is approximately equal to 0.000 something. What are you? Very silly, right? Similar problem is that here. This problem says the weight that the piece can sustain before breakdown is normally distributed with mean 400 and standard deviation 4. This 400 actually 400 what? In the unit of 1,000 pounds. So 400,000 pounds. Average is 400,000 and standard deviation is 40,000 pounds. Now suppose that a single vehicle weighs, the average weight is 3,000 pounds. That means 1,500 kilograms and 0.3. How many cars could be on the bridge, but it will not change? Okay, how many cars is required to exceed the probability 0.1 that the bridge will be 10? So similar thing, just this time, our calculation will be value of n. How many cars is there? In this case, we calculated the probability, but here, when things are given, we need to calculate the value of n. So, I'm not solving this one. Very simple. You know it. We solved this type of problem before. Approximation of binomial random variable. If I tell you the binomial random variable has the approximately normal distribution, you will agree or not? Binomial distribution has approximately normal distribution. Let's say x1 to xn are Bernoulli random variable. Then their sum is what? X. X is what? X1 is the success in one Bernoulli experiment. Then X is what? Total number of successes in Bernoulli experiment. And that is what? Then X represents what? Number of successes in n processes. Then X is binomial. But according to the central limit theorem, X is what? So we can say this X is approximately normal with mean value is, what is the mean value of binomial NP? What is the average of the standard deviation of the binomial? NP times 1 minus P. So X is, in principle it is binomial. But here it is approximately normal with average value NP. Then we can further write x minus NP divided by square root of NP times 1 minus P is what?
Standard.
Approximately standard. And we can use the table. Ideal side of the first year class. Very interesting problem. Problem X. Let me set in some terms. First year class at a particular college is 150 ideal size. Now, the college knowing from the past experience that on average, only 30% of those accepted for admission will eventually get it. You understand that? Now, I will look at it say. If we want to get admitted 700 students, then actually this year goes up to what? That means 30% or an average 30% of the students get admitted. Remaining, say, go to Kuwait, university, medical, other universities. Okay. So, knowing that one, that 30% will only 30% will accept the admission offer. Uses a policy of approving the applications of 450 students. Instead of doing what we do here in IoT, we first call 600, 700, then if 200 gets admitted, then we call next 500. Out of this 500, 150 get admitted, then we call 350. What they do, knowing that it is the general practice that only 1/3 of the students will get admitted, they call 400 students. Question is, what is the probability that more than 150 students will? If more students come, then you cannot actually reject them. Then in that class, more than 150 students will be there. What is the probability? This probability is first forget this portion. I am coming here. Actually, what we want to know, X is greater than 150, right? But instead of 150, what they did, 150.5. What? Actually, since X now in normal random variable, you cannot calculate the probability that a continuous random variable X has a value 150. That's why what they did, for X is equal to Xi, this probability actually is the probability that I is in between 0.5 to I plus 1. That means this one actually is x is greater than 0.5, but instead of writing x is equal to 150, what we can write with probability that x is in between just it is an approximation to the basically to the that's why instead of writing that x is greater than 150, they have written 151. Now, what is this? This x is approximately normal where then this x should be subtracted by n has a value 450, p has a value what? 0.3. 450 times 0.3, 450 times 0.3, 1 minus p is 0.7. And this one becomes z, is standard normal, and here it becomes 1.5 pence. So it is approximately equal to probability that z is equal to 1.59. And from the table, it will be approximately equal to 1 minus probability that z is less than equal to 1.59 and equal to 1 minus phi of
1.5.
then we have a value of 1 minus 0.94, which is equal to
0.06.
so let us finish here.